In this video, I'm going to be introducing the concept of logic and reasoning. There's two particular types of reasoning that we're going to be looking at. We have inductive reasoning and we also have deductive reasoning. Deductive reasoning, which we're not going to be covering in this video, is more of the stronger type of reasoning. That's the type of stuff that we'll be using to create proofs a little bit later on. Inductive reasoning is more of a weaker type. We can't quite use this to write proofs. However, most of the things that we're going to end up writing proofs with and using that deductive reasoning, they begin by applying inductive reasoning. Inductive reasoning is mostly looking at patterns that we see and coming up with ideas about those patterns. Okay? A conjecture is an unproven statement that's based on observations. Inductive reasoning is the act of finding a pattern in specific cases and then writing a conjecture for the general case. What that means is that we start with this process of inductive reasoning and looking at some pattern, whether it be a physical pattern that we see here with shapes, or maybe a pattern with numbers, or it could be just something in our general life that we notice. Okay, and when we see that pattern, we start to process a rule that goes along with it. That rule is the conjecture. Example one is a literal pattern. What we're going to be asked to do here is take a look at the figures that they have provided and then create a fourth figure. To create that fourth figure, what we need to be able to do is describe that pattern. Okay, so we're going to observe what we see here. Okay, as you move along from one circle to the next, you're definitely going to notice that you have less shaded region. Okay, it's going to become less as you move along. But how do they actually do it, and how do they determine where we're going to shade those regions? How does all that look? All right, let's go ahead and start making some observations about these figures. As stated before, the shaded region is becoming less in each of the figures as you go along. In fact, you could write each of these as a fraction because it appears that the individual pieces that you have in each one of these are all going to be the same size. We'll go ahead and work under that assumption. Okay, so in the first picture, you've got 1 out of 2 pieces being shaded. In figure 2, you've got 1 out of 4 pieces. Figure 3, you've got 1 out of 6 pieces. Okay, so mathematically, you might actually see a pattern here that you're going from 1/2 to 1/4 to 1/6, and then you could probably imagine that the next is going to be 1/8. All right, 1/8 of the next figure is going to be shaded. Now, with that in mind, we need to think about where is it actually going to be shaded. All right, so some things about how these are divided up here. Let me go ahead and draw a circle so I have one ready. All right, so let's really start thinking about how these are divided up. In the first, you got 1 out of 2, so you had 2 equal sized pieces, 1 out of 4 for the next, so you had 4 equal sized pieces, and so on for there. When we do divide these up, though, there's a little thing that I didn't notice, which is that no matter which picture you look at, you do have a horizontal line that's in there. Okay, so there's that horizontal line, then you have it and you cut it. But once you move to the sixth figure, you can't actually have the horizontal and the vertical with it. You know, that's not the pattern that we have here. There's other patterns that might exist where maybe you divide up each of those and so on, but we actually have this 1/6 here. So it looks like the horizontal line is staying put, and then all the rest of them are going to just sort of just around it, evenly divide up the rest. Okay, so for this figure, I'm going to go ahead and keep with having that horizontal. This one would have a vertical. You would need to go back to having a vertical like in that picture. And then we can divide up those 4 sections and you get 8 equal sized pieces in there. And we're maintaining that horizontal there. So then when we start talking about the shaded part of it, you could, in the first, you just say it's the top half. That's it. When you move to figure 2, you kind of rephrase it now as it's in the top half, but it's to the left. Okay, and you can actually use that description for the third figure as well. It's in the top half and to the left. Okay, so for the last picture, let's go with the same thing. It's in the top half and it is to the left. So it would end up being that region that we have there, at least based on the 3 figures that we've seen. As mentioned before, inductive reasoning is one of our weaker types of reasoning, so you've got to base your conjecture on what you do see. So given three figures, I believe that this is the best image we could come up with the fourth. But sometimes, like if we only gave you two figures, you're probably open to a different interpretation for the third one. So given what we have here, I think that this is going to be the best choice. Now, as far as describing this in words, I'll sort of leave that up to you. Like you decide what types of things that you want to mention as you describe this. You can talk about adding two more spaces so they're all equal. You could talk about maintaining that horizontal line if you want. You can even describe it, this is an interesting one here, you can even describe it as adding an extra line, right? This one has one line, that one has two, this one has three, that one has four. So maybe you could describe it as making sure that you have one more line from picture to picture with all those lines equally spaced and maintaining a horizontal. So lots of different things you could say about this figure, and I'll leave that up to you. In example 2, we're going to look at a number pattern. We have a sequence of numbers here. You are going to notice that there's 4 values there. Okay, so as I was kind of mentioning in the above problem, if you end up limited with the amount of figures or values that you have to start your pattern with, sometimes you can go into different directions on how you interpret that pattern. So the more that you have at the beginning, the more likely it is that you will pick out the pattern that is actually being presented here, the one that the writer of this sequence would want you to know. All right, so we're going to figure out what the pattern is, and we are going to produce the next 3 numbers in the pattern. Okay, the next 3 values that would go here. All right, where I think your attention is mostly going to go will be these smaller numbers that we have at the front here. We've got the 7 and the 21. Okay, as you move into larger numbers, we don't know as much about them. But between these two, one thing that we should pick up on here is that 21 has 2 factors in it, and those factors are 7 and 3. So we should be able to notice that if we go from 7 to 21, we can multiply by 3. You can multiply by 3. Okay. Now, does that hold true as we go from 21 to 63? And yeah, when you multiply by 3, 3 times 1 is 3, 3 times 2 is 6, you get 63. So again, you're multiplying by 3. And you can check over here and see that that also is multiplying by 3. 3 times 3 is 9, and 3 times 6 is 18, so you get 189. Except there's the obvious thing here of a negative number. Well, a couple of negative numbers that we got here. We actually start with the -7, and then we add -63 there. Okay, so how can we work that part into multiplying by 3 as you go along? Well, instead of multiplying -7 by 3, which would give you -21, you can actually just multiply it by -3. If you multiply by -3, you're going to cancel out that negative and get a positive 21. You can then repeat that pattern. You can multiply again by -3. Actually, I'm going to take out these x's because I think that doesn't look as clear, and just use parentheses to indicate the multiplying. Positive 21 multiplied by a -3 is going to give you -63. Okay, so when you're multiplying by a negative number, it will cause your signs to flip. Okay, so then once again, multiply by -3 and you get positive 189. All right, so to continue the pattern, we'll take 189, multiply that by, I'll just multiply by 3. It is going to be a -567. Okay, so I'll just keep track of the negative sign because it just flip-flops as you go. Times that by 3. This one will be a positive 1701. Times 3 again, we're going to get negative 5,103. Example number 3 is going to introduce something that may be new to you, which is consecutive integers. Consecutive means back to back or one after another. For example, 4 is one number right after 3, and then 5 is one number right after 4. Okay, consecutive integers. Integers, though, to be clear about this part here, integers are going to be anything that would be like a whole value type number, including all the negatives and even 0. So if you were to draw a picture of a number line, typical number line, imagine that, and you place a 0 in the middle, and then you start marking off 1, 2, 3, 4, 5. Other direction, you mark off -1, -2, -3, etc. That basic number line without any of the half value numbers and stuff, those would be your integers. Okay, whole values that are positive or negative and also 0. What we're going to do is make and test a conjecture about the sum, that would be addition, the sum of any 3 consecutive integers, right? So 3 plus 4 plus 5 is going to turn out to be, let's see, 7 plus 5 is 12. You're going to get 12. Okay, that would be the sum of 3 consecutive integers. Now I could make up another example. Let's do 8 plus 9 plus 10. And that one would be 17 plus 10, which is 27. All right, and now what you're going to want to do is try and get creative. I'm going to hint to this, the integers part here. Try and get creative and come up with a couple more examples. And then see if you can create a conjecture that goes along with the sum with respect to the values, of course, that we start with. Here, I'll toss out another one here. Let's say -3 plus -2 plus -1. We'll put some parentheses in there to clean it up. Okay, these are consecutive integers. They are back to back, and I still have them in increasing order, like these are here. That sum, being that these are all negative numbers, is going to be -6. Okay, so there's 3 of them for you. You can create as many more as you need, but what you want to do is think about the sum part, think about the 12, the 27, the -6, and see if you can create a conjecture about that sum with respect to the numbers that you begin with. I hope that you did come up with a couple extra examples that you could use here. Just anything that's a little bit different than what I have, more examples, the better it is for coming up with an idea. And once you did that, usually the first observation that we make is all the numbers that we come up with are divisible by 3. Now that might be hard if you chose like really large numbers. Let me add one more on here. Let's do, actually this one, yeah, we'll do this. 28 plus 29 plus 30. Okay, and now if I add all of those together, might need a calculator just to make sure I even do that one right. All right, 28 plus 29 plus 30 is going to give me 87. Okay, so that one might not be as obvious that it's divisible by 3, but if you do enough of them, that might be the first thing that you realize. All of these are divisible by 3. Okay, so what is 12 when we think about 3 multiplied by a number? Okay, that would be, well, 12 divided by 3 will give you 4. Okay, and then the next, if I took 27, divided it by 3, about to write 27, that's not what I want. If I divide it by 3, then I would learn that, okay, well, 3 times 9 is what makes that number. Okay, -6 is also divisible by 3, so that could be 3 times -2. All right, and last, 87. We might not recognize it, but based on all the other ones, we would run a little test here and say, all right, 87 divided by 3 is 29. 29 times 3 is 87. And now, let's take a look at this versus what we see from the consecutive integers. 4 is right there, and 9 is right there, and -2 is right there, and 29 is right there. It ends up that all of these numbers are actually the middle number within the consecutive integers. So here could be our conjecture. The sum of 3 consecutive integers is 3 times the second value. 3 times the second value. Okay, now how does it really work out? Why is that true? Let's take a look at the one that we've got here. If I decrease the 5 by 1, drop that down to a 4, I could then take that 1 that I removed from it add it on to the 3, like redistribute some of the numbers here. Take 1 from the 5, redistribute over to the 3, and I would actually have 4, 4, 4. 4 times 3 gives you 12. And the same thing here. You can take 1 away from 10, add it to the 8, and you'll have all 9s. You can even do that here. It's a little bit maybe weirder with the negative values. But look, around -2, you've got a balance of a number that's 1 greater and 1 that's less. Okay, and then even over here, you could take 1 from the 30, move it to the 28, and you've got all 29s. So again, your conjecture here could be that the sum of 3 consecutive integers is going to be 3 multiplied by the middle number. And then you can come up with all kinds of other fun answers. Restate this, the sum of 5 consecutive, let me spell that, 5 consecutive integers. I won't write that word there, but you could try and figure out what that would look like. And then you can even start looking at maybe doing something with evens. The sum of 4 consecutive integers, and see what that one turns out to be. So there's a lot of really cool ones that you can come up with based off of the one that we have seen now. Last, what we have is counterexample. A counterexample is a specific case for which the conjecture is false. Okay, so for example number 4, we're going to be given a conjecture which is going to sound pretty good at first, but there is a flaw in it. It ends up that flaw, if you just tweak it a little bit, you change up the conjecture just a little bit, then it will actually be true. This will be a true conjecture. All right, so this one says that the sum of 2 numbers is always greater than the larger number. Okay, so what that means is if I took 2 numbers like, let's say 3 and 8. If I take 3 and 8 and I add them together, okay, so again, that's the sum. If I add them together, I'm going to get 11. Okay, so our statement says the sum of 2 numbers, which would be the 11, is always greater than the larger number. So they're referring to the 8 here. The sum, 11, is bigger than the bigger number that you got here. And where that idea comes from is when we add numbers together, we get bigger things. That's how we're taught addition in elementary school. When we add numbers together, we get something bigger. However, it is not always true. It is not always true. Why is that? All right, in this case, it doesn't specify what types of numbers we have to use. So if we're just thinking about what we call the natural numbers here, if you're just thinking about the natural numbers, that statement would be true. But if we leave this open to be any 2 numbers, we've got to consider our integers. We have to consider integers. What if we had negative numbers? Okay, what if we had -3 plus 8? Well, when you add those together, you get 5. And 5 is not greater than the larger number here, 8. So this would be called the counterexample. It tells us that this statement is not true, that the conjecture is false. Look, you can even do another one and do maybe 0 plus 8. 0 plus 8 is 8. Okay, so in this case, that one is actually equal than the larger number. So right here, they're making the claim that it's always going to be greater. Well, it will always be greater if you take the sum of 2, we call these natural numbers. If you take the sum of 2 natural numbers, that will always be greater than the larger number that you start with. That would be true. All right, so natural numbers are starting at 1. They're going to be all the whole values starting at 1. Integers will then include the 0 and all the negatives.
Later, blah.